Section 5.4 is on page 211, talks about the famous Euler equations. So not one, many of them. And regular singular points, that's a side note. But Euler equation, number 10. X squared, if you happen to have an x squared, an x, and a constant, that reminds you of what? Quadratic in x, and y prime and y double prime, linear in differentials. So linear differential equations with non-constant coefficients, where alpha and beta, those are actually numbers. If that's the case, he said, if you see it that way, let y equal x to the r, that will work. And for convenience, do keep in mind, if you wanted to make this look like a traditional problem, you know what I mean by traditional? What we've been doing on every single section, wouldn't you divide? And do you see what they're choosing? Obviously, because x is not analytic at x equals 0. Now, something to keep in mind, if I take a derivative of x to the r, you bring the power down, subtract 1 from the power. And if you take another derivative, you bring the power down, subtract 1 from the power. There's something I want to show you that, I'm not sure if it's in the book or not, but here it is. I want to show you if I have x raised to the a plus bi, plus or minus. So keep in mind, we know how to deal with e raised to the a plus bi. If you remember e to the a plus bi, we said that's e to the a times e to the bi. That is e to the a, and this is the cosine plus I sine of b. Well, here we have a problem because this is not exponential. So what we do, we say, all right, we can make that exponential. Property of logs. And wouldn't that be e to the a natural log of x plus b natural log of xi? Wouldn't that be e to the a natural log of x times e to the b natural log of xi? Now, can't I reverse this? And wouldn't that just be x to the a? And isn't this matching the Euler formula? Isn't e to the I theta the cosine of theta plus I sine of theta? So, wouldn't that be the cosine of b natural log of x plus I the sine of b natural log of x? So wouldn't you say x to the a times c1 the cosine of b natural log of x plus c2 the sine of b natural log of x? I just want to show you that because that's how every answer looked like, and you need to know where that comes from. So basically, if I see x raised to the a plus b, the solution will be x to the a, and that b right there would pick a b natural log of x for the sine and cosine angles. So now let's look at some problems. I'm looking at problem number 4, and I notice this matches. If this is the case, I'm gonna let y equal x to the r. I need a derivative of that. So this is a linear differential equations with non-constant coefficients. Y equal e to the x doesn't work, or not guaranteed to work, let's put it that way. And the only problem you could run into if x happened to be 0, but they eliminated that because our assumption all throughout is that x is either positive or negative but not equal to 0. Now if I substitute, if I take, I'm looking at x squared times r into r minus 1, x to the r minus 2, minus x times y prime and, of course, the famous y And what happened when I multiply those? Don't you add the powers? When you multiply those. And what do you think happens? Well, Euler again. Isn't that r squared minus r? That's this. Minus r plus 1. Well, x to the r can never equal 0 because of our assumption. X is either positive or negative. Which means it must be that r squared minus 2r plus 1 must equal 0. Or r minus 1 squared must equal 0. So r equal 1 multiplicity 2. So here, determine the general solution of the differential equation over the valid interval, and that's exactly what we're going to do. We're going to say y equal some c1 x to the 1 plus c sub 2 x to the 1, and in this case we multiply by natural log of x. So the fundamental set is x to the 1, x to the 1, but those are not linearly independent. So you multiply by natural log of x to make them linearly independent. That's repeated. And if I look at problem number 2, same deal. Let's tackle that out. I noticed that this is x plus 1, not x, x plus 1. Can you guess what I'm going to let y equal? X plus 1 to the r. The derivative of that will be r into x plus 1 raised to the r minus 1, and the second derivative will be r into r minus 1 x plus 1 to the r minus 2. So I would replace this, not this. This is actually x plus 1 squared. Y double prime is r into r minus 1 into x plus 1 to the r minus 2 plus 3 x plus 1, and y prime is right there. That is r into x plus 1 to the r minus 1 plus 0.75, that's really 3/4. And y is right there. That would be x plus 1 to the r equaling 0. And again, I could take those and multiply them. I'll be looking at r squared minus r times x plus 1 to the r plus 3r, and if you multiply those, that's x plus 1 to the r plus 3/4 x plus 1 to the r equals 0. Factor out x plus 1 to the r. That would be r squared minus r plus 3r plus 3/4. And we know that, again, keep in mind, if I was to divide by this, do you see that x can never equal negative 1? So x plus 1 to the r can never equal 0. Because we're going to choose, before we chose x to be bigger than 0, here we're going to say x is either bigger than 1, negative 1, or less than negative 1. So this can never equal 0. So it has to be that r squared plus 2r plus 3/4 equal to 0. Let me make sure that is right, that is right, that is right. And I'm looking at 4r squared plus 8r plus 3 equal to 0. That factors into 2r plus 1 into 2r plus 3. That is 4, 6, 8, yep. So r equals negative 1/2 or negative 3/2. So my solution out of this is y equal c sub 1 into x plus 1 to the negative 1/2 plus c sub 2 into x plus 1 to the negative 3/2. And that would be the general solution. So we're taking on all three cases. We're not going to really go in depth with that because it's not really that much different. And here we go back, say, look, that happened to be x. We're going to let, can you guess, y equal x to the r, and of course a derivative. By now, hopefully that's becoming a bit easier. R into r minus 1, x to the r minus 2. And if I substitute 2x squared times r minus 1, x to the r minus 2, minus 4x times r times x to the r minus 1, plus 6 x to the r equals 0. If I multiply those twice, and if I multiply that, r squared minus 2r times x to the r minus 4r times x to the r plus 6x to the r equals 0. So here, if I factor x to the r out, I'm looking at 2r squared minus 2r minus 4r plus 6 equal to 0. X to the r can never equal 0. I have 2r squared minus 6r plus 6 equal to 0. And here, if I try to work this out, I'll be looking at r squared minus 3r divided by 2. Move this to the other side, that's negative 3. And if I take half of the middle number, which is 3/2, and square it, that's 9/4. That will be r minus 3/2 squared equaling, this is negative 12 minus 9 is negative 3/4. So r will equal 3/2 plus or minus radical 3 over 2i. And we know how this works. The solution is going to be x to the 3/2 from what we started this section with, and it's going to be c1, the cosine of radical 3 over 2 natural log of x, plus c sub 2, the sine of radical 3 over 2 natural log of x. And there it is. And again, you could derive what I did. Even here, you could derive it by following these steps. Keep in mind that a raised to the log base a of x is x, and vice versa. So you could go forward and you could go backwards. Just remember that part. And things will work out nicely. The second portion of this section is really straightforward, something that we're going to use a bit, and this is what it says. Again, keep in mind the main player for us. If that's a 1, there's your P, there's your Q. Let x sub 0 be a singular point. If the limit as x approaches x naught of x minus x naught times P of x is finite, meaning the limit exists. And if the limit as x approaches x sub 0 of x minus x sub naught squared times q of x is finite, then the singularity is called a regular singular point of equation 1. That's equation 1. So they want us to check how this works, find all singular points of the given equation, and determine whether they are regular or irregular. What's regular? If you get both to be a finite. So first order of business, you make sure that's a positive 1. It's not y double prime plus 1 minus x over x, y prime plus y equal to 0. So in our case right here, P of x is right there, and Q of x is right there. That's a 1. So what I need to do, I need to take the limit as x approaches. In this case, do you see what point you're not allowed to have? That's how you get x naught. Of what? Of x times, this is raised by x because that's a 0, P of x. P of x is 1 minus x over x. Find that limit. Wouldn't these two cancel out? Wouldn't that be a 1? That's good. And what's the limit as x approaches 0 of x squared times 1? Isn't that a 0? So since both of those are finite, we say this is regular. A regular point. Non-regular if one of those limits don't exist. The same deal happens here. This is not a positive 1. I ensure that's a positive 1. That's going to be our case all throughout this class. Now here, there is some simplifications to do. This is 1 minus x squared, 1 plus x squared. This is 1 minus x squared, 1 plus x squared. Okay, this cancels with one of those. You pick a negative, right? Simple algebra. That is x over 1 minus x into 1 plus x squared. This cancels with one of those. You're left with 1 over 1 minus x squared times 1 plus x, y equal to 0. So we know this is, oh boy, we know this is p, and we know this is q. So if I take out of those the limit as x approaches 0 of x over negative x over 1 minus x into 1 plus x squared, I'm going to multiply that by what? I'm going to multiply that by x minus, and I have a few things to really worry about. I'm going to take that, let's say we're talking about x equal 1. We have two values, right? For x equal 1, I'm going to multiply that by x minus 1. What would happen? This will cancel with that. That will become a plus. I'll get 0 over 1, which is 0. I'm sorry. X approaches 1. I'll get 1 over 2. I'll get 1/4. And that will check. And if I take the limit as x approaches 1 of q is 1 over 1 minus x squared times 1 plus x times x minus 1 squared. Those two undo each other, and I'm left with 1/2. So therefore this is a regular. And if I let x equal negative 1, so these are the only two singularities, x equal negative 1, I would take the limit as x approaches negative 1 of x over 1 minus x, 1 plus x squared multiplied by x plus 1. This will cancel one of those. I would be left with a negative 1 over 0, which is infinity or negative infinity, meaning it does not exist. Since one of those does not exist, automatically this is irregular. And there's my homework.